Welcome to Algebra Readiness for students in grades 6 through 9. It is one thing to see threads of algebraic thinking in a student response, or to notice gaps in thinking. It is quite another thing to know how to teach the student to develop his or her thinking in productive ways. The goals of this video are to help you increase your students' understanding of algebraic concepts and develop their algebraic thinking in productive ways by analyzing tasks, implementing high cognitive demand tasks, and assessing student thinking. These goals will be accomplished by looking at the cognitive demand of tasks, the algebraic habits of mind, the maintenance of cognitive demand, lesson planning, and questioning techniques. Here are 4 tasks. Take a moment to read them and think about how they are the same and how they are different. They all have something to do with multiplying fractions, yet each is engaging the student at a different level. The thinking required to complete each task is different. As the previous 4 examples showed, not all tasks are created equal, and different tasks will provoke different levels and kinds of thinking. Why is this important? The level and kind of thinking in which students engage determines what they will learn. So let's begin by talking about how to choose a good task. What criteria should we look for? Analyzing tasks, cognitive demand. One aspect of analyzing a task is examining its cognitive demand. But first, let's clarify what we mean by a mathematical task. Mathematical tasks are a set of problems, or a single problem, the purpose of which is to focus students' attention on a particular mathematical idea. You will see several examples of tasks as we move through this presentation. There is no decision that teachers make that has a greater impact on students' opportunities to learn, and on their perceptions about what mathematics is, than the selection or creation of the tasks with which the teacher engages students in studying mathematics. Think about the power of this statement. The tasks you choose not only impact the students' opportunities to learn, but impact their perceptions about what mathematics is. Therefore, selecting high-quality tasks is one of the most important decisions you as a teacher will make. So how do you determine whether tasks are of high quality or not? There are multiple ways to examine a task. You could look for the number and kinds of representations evoked. For example, to solve a task, students may create a table of values and a graph to represent a mathematical situation. Another way to examine tasks is to think about the variety of ways the problem could be approached. Or you could think about the requirements for communication. Do students have to write about their thinking process? Do students have to share with others how they solve the problem? Another way to examine a task, and the one we're focusing on here, is to analyze the cognitive demands of the task. What do we mean by cognitive demand of a task? We mean the kind and level of thinking required of students in order to successfully engage with and solve the task. When characterizing the cognitive demands of tasks, we can classify them as low-level tasks or high-level tasks. A low-level task is one that merely requires recall of memorized facts or completion of a procedure that has no connection to the underlying concept. A high-level task, on the other hand, might ask students to make connections between a procedure and its conceptual basis. These connections not only help the student make sense of the procedure, but increase the likelihood that it will be recalled and used appropriately. Another type of high-level task involves what is called doing mathematics. When students do mathematics, they are actively involved in exploring, investigating, modeling, conjecturing, and verifying. Doing mathematics requires complex and non-algorithmic thinking. Let's take a look at tasks that illustrate these four types of cognitive demand. This task is one that merely requires recall of a rule. There is no connection to the concept of multiplying fractions. This task requires the use of a rule, but again, there is no connection to the concept of multiplying fractions, and the emphasis is on finding the correct answer. No explanation is required, and there is no expectation of understanding. In this task, students' attention is focused on developing a deeper level of understanding of multiplication of fractions through the use of pattern blocks and drawings. A task such as this, that encourages multiple representations, will enhance students' conceptual understanding of the procedure for multiplying two fractions. This task requires student engagement, not mindless manipulation. Here is one example of how a student might approach the task. The student is considering two hexagons to be the whole. The figure on the left shows half of the whole, or one of the hexagons shaded. Next, the student needed to find 1/6 of that 1/2. The figure on the right shows how the student divided the hexagons into triangles to find that 1/6 of 1/2 is 1/12. The student explains his reasoning this way. First, you take 1/2 of the whole, which would be one hexagon. Then you take 1/6 of the half. So I divided the hexagon into 6 pieces, which would be 6 triangles. I only needed 1/6, so that would be one triangle. Then I needed to figure out what part of the two hexagons one triangle was, and it was 1 out of 12, so 1/6 of 1/2 is 1/12. This task helps students to make meaning of the procedure for multiplying two fractions. This last example asks students to create a real-world situation for a fraction multiplication problem. Then, they have to solve the problem without using the rule for multiplication of two fractions, and explain their solution. This task requires more cognitive effort than the previous ones, because the student must truly understand multiplication of two fractions in order to write a word problem that illustrates this concept, and then solve the problem without using the traditional approach of applying a rule. This requires considerable cognitive effort and helps students make a connection between the concept and the rule. This task is open-ended and does not suggest a predictable approach, thus allowing for multiple access points. One student wrote this word problem for 2/3 times 3/4. For lunch, Mom gave me 3/4 of the pizza that we ordered. I could only finish 2/3 of what she gave me. How much of the whole pizza did I eat? Then he drew a rectangle to represent the whole pizza, and shaded the 3/4 that his mom gave him. He then figured out what 2/3 of the 3/4 would be. The student explains his reasoning this way. I drew a rectangle to show the whole pizza. Then I cut it into fourths, and I shaded 3 of them to show the part that Mom gave me. Since I only ate 2/3 of what she gave me, that would be only 2 of the shaded sections. Notice how the student used arrows to show the part of the pizza that he ate. This task is open-ended, thus allowing for varied approaches. By allowing students to access and use their prior knowledge to solve this task, multiple solutions will arise. Through sharing of these solutions, students will learn from one another. The task also allowed students to make connections to real-world situations they created. Often, a task may appear to be of high cognitive demand because of superficial features such as the use of manipulatives, of real-world context, or because it requires multiple steps. These aspects alone do not raise the cognitive level of a task. Remember, it has more to do with what the student is being asked to do. Another consideration when choosing a task is to consider the prior knowledge and experiences of your students. These can impact the cognitive demand of a task as well. Also, the norms of the classroom are important. If students feel comfortable taking risks and making mistakes, then the cognitive demand of the task can be maintained. but we'll discuss that in depth later. Analyzing tasks. Algebraic habits of mind. Cognitive demand is only one way to analyze tasks. Another way to analyze tasks is for the algebraic habits of mind that they elicit. Don't let the title Algebraic Habits of Mind fool you. Although algebra is a course that's typically taught in grades 8 and above, the habits of mind that are needed to become a successful algebra student begin in earlier grades. Let's consider our typical approach to teaching. In this cartoon, the first boy says, "I taught Stripe how to whistle." The second boy responds, "I don't hear him whistling." The first boy says, "I said I taught him. I didn't say he learned it." As a teacher, you may often feel this way. In the field of algebra, we often teach things to students that include a procedural approach to algebra, but students fail to understand the true nature of algebraic thinking. Algebra is not about a set of mundane procedures, but about the structure and patterns of numbers and the relationships among them. Like Stripe learning to whistle, all students need the opportunity to engage meaningfully in learning algebra, rather than merely watching someone else do algebra. That is, students need to develop ways of thinking and doing algebra, called algebraic habits of mind. So what are algebraic habits of mind? Essentially, they are the habits of applying productive lines of algebraic thinking whenever working on a mathematical task. They are the common ways of thinking that students need to develop to learn algebra meaningfully and to be able to apply algebra to mathematical situations. In developing this framework, Mark Driscoll and his colleagues at the Educational Development Center have identified 3 specific habits of mind that lead to understanding and using algebra in meaningful ways. These habits of mind include doing and undoing, building rules to represent functions, and abstracting from computation. Let's take a deeper look at what each of these mean. A central tenet of the doing and undoing habit of mind is reversibility. In algebra, reversibility plays a central role because students need to be able to undo mathematical processes as well as do them. In other words, students must understand the process well enough to work back from the answer to a starting point. At the high school level, students are often asked to solve equations, like the quadratic equation x squared minus 5x plus 6 equals 0. Using factoring and knowledge about products that result in 0, an algebra student can solve this equation to find the solutions 2 and 3. However, students that exhibit algebraic reasoning not only can solve this equation, but they can also work backwards. That is, if they are given the solutions x equals 2 and x equals 3, they can find the quadratic equation that has these 2 solutions by undoing the procedures they would use to find the solutions. So what does this mean for students and teachers of grades 6 through 9? The processes of doing and undoing, and the act of considering reversibility should begin in the elementary grades and continue throughout a student's academic career. As teachers consider the types of mathematical tasks to give students, it's important to evaluate whether the task could be phrased differently to provide a foundation for doing and undoing. Let's consider some examples of mathematical tasks that have the potential to elicit the doing and undoing habit of mind. Students are often asked to find the mean of a data set, but consider this problem. Find a set of 5 numbers that have a mean of 56. In this problem, students must work backwards to find a number. Here's another example. Find 2 different positive real numbers with a sum of 1/11. In this task, students must consider fractions that are equivalent to 1/11, such as 3/33, and consider the 2 numbers that can sum to 3/33, such as 1/33 and 2/33. Finally, for approximately what values of x will the graph of y equals x squared minus 7 have a height of 100. In this problem, students must reason about the output of a function, 100, to consider the possible inputs of the function. This kind of thinking is the reverse of the typical function problem that moves from inputs to outputs. Students can estimate possible answers as being between 10 and 11, or alternatively between negative 11 and negative 10. Another solution strategy would be to find the exact values of plus or minus the square root of 107. Visual models can often provide meaning for algebraic expressions. For example, area models can be used to help one to see why the quantity a plus b squared equals a squared plus 2ab plus b squared. Often, these problems give students the expressions being multiplied, and students find the corresponding areas. Let's see how area models can be used to elicit the doing and undoing habit of mind. Mr. Brent Smith is an Algebra 1 teacher at Winchester Community High School in Winchester, Indiana. Mr. Smith uses area models to help his students make sense of algebraic expressions. Let's examine how he presents a problem that could help students to utilize a doing and undoing habit of mind.
If the area of the entire rectangle is 300, what is the missing dimension? This is kind of working backwards from what you've seen pictures like this before. Think about what it would take in order to find that missing dimension based on what's given to you.
By posing the task so that part of the side is unknown, students must use what they know about the other sides and the areas to solve the problem. The second algebraic habit of mind is building rules to represent functions. Functions play a central role in the algebra curriculum, and the ideas that motivate the development of the concept of function begin in the elementary grades. In the middle grades, these ideas include seeing and predicting patterns, describing and justifying rules that describe numeric relationships in a context, and describing change using different representations. Students in middle and high school are expected to analyze situations and determine whether the situation describes a linear, quadratic, exponential, or other type of function. Let's demonstrate with an example. Andy is saving money for a new DVD player. He began saving with a $5 gift and will continue to save $2 each week. How much money will he have saved at the end of n weeks? One possible solution strategy may be to organize the information into a table. Andy begins with $5. After 1 week, he will have $7. After 2 weeks, $9, and so on. Algebraic thinkers can look for patterns in such problems, like the fact that there is a common difference of 2. By noticing the change in the numbers as constant, one can realize that the situation describes a linear function. Since the initial amount was $5 and the change is $2, after n weeks, Andy will have saved $5 plus 2n. This describes a linear function with a slope of 2 and a y-intercept of 5. Here's another task that can be used to elicit the building rules habit of mind. Eric was one of a number of sheep rounded up to be shorn. On one particular day, there were 25 sheep waiting to be shorn. Eric was at the back of the line. Eric decided that he would not wait his turn. Each time the shearer had shorn one sheep, Eric would sneak past 2 other sheep in the line. How many sheep will be shorn before Eric gets his turn? In this problem, students must look to describe a rule and predict future values based on the generalization of the pattern. Consider another example. When I placed the bag of popcorn in the microwave, the volume of the bag was very small. After pressing start, the bag's volume did not change for several seconds. Then, suddenly, as the kernels began to pop, the volume increased rapidly. Finally, once most of the kernels had popped, the volume of the bag did not change. Draw a graph in the xy plane that shows the relationship between time and the volume of the bag. In response to this item, students may describe the change that takes place as being gradual in the beginning, speeding up, and finally leveling off. Such thinking can be used to informally introduce the concepts of rate of change and slope. Being able to describe change in a process or relationship between variables is inherent to the building rules habit of mind. Ms. Tricia Shoemaker is a junior high mathematics teacher at Monroe Central Junior-Senior High School in Parker City, Indiana. One way that Ms. Shoemaker incorporates the building rules habit of mind into her instruction is by using real-world situations such as this grocery store task. The task requires students to consider how shopping carts are nested together in grocery stores. They also have to incorporate the concept of scale factor. Rashid is planning the layout for a new grocery store. He found the diagram shown in a supply catalog. It shows a drawing of a single shopping cart and a drawing of 12 shopping carts that are nested together. The drawings are 1/24 of the real size. Rashid has several questions. Number 1, what is the length of a real shopping cart? Number 2, when the real carts are nested, how much does each cart stick out beyond the next one in the line? Number 3, what would be the total length of a row of 20 real nested carts? Number 4, what rule or formula could I use to find the length of a row of real nested carts for any number n of carts? Number 5, how many real nested carts could fit in a space 10 meters long? The last question is an example of doing and undoing, just mentioned as another algebraic habit of mind. After students have solved the problem, they are to write a letter to Rashid that answers his questions and provides an explanation for each answer. Let's see how Ms. Shoemaker prepares the students for working on the task. Take notice of how she makes sure the students use the proper unit of measurement and answers any questions the students have about the task before they begin working.
So first of all, looking at your ruler, if question 5 wants a 10 meters long space, what are we going to measure in? Inches or centimeters? So you always have to read the whole problem first to make sure you know what you're looking for. Okay, any questions? Yes?
Do you want us to measure the shopping cart from like the bottom or from
You want the whole shopping cart. So as a group, you guys can discuss and decide that. All right, things to remember. Make sure you show your work. Remember, an answer is not good enough. I want to know, how did you get the answer? You got to be able to justify your answer at the end. So make sure you're writing down how you got your answer. And then down at the bottom, when you get done as a group on 1 through 5, everybody's answer at the bottom should be their own work. Write a letter to Rashid that answers these questions. So the part at the bottom should be in your own words, and you can work it on the back. All right, any questions? All right, begin.
This task was introduced after students had already completed similar tasks that involved building rules to represent functions. For this task, the students not only had to find a rule for finding the length of a row of real nested carts, they had to explain their answers to the questions in a letter to Rashid. By incorporating the communication of results into the task, each student was held accountable for understanding the solution. A third algebraic habit of mind is abstracting from computation. This includes students' abilities to generalize beyond examples, calculate without computing, recognize and represent equivalent expressions, and justify computational shortcuts. Driscoll has described this as the capacity to think about computations independently of the particular numbers used. Many of the properties used in symbolic algebra, such as the commutative property, the associative property, and the distributive property, can and should be developed as students learn about numbers. In middle and high school, our hope is that students can rely on number sense developed in elementary school to reason algebraically. For example, students should be able to identify which number is larger, 5% of 7 million or 7% of 5 million, without actually computing both percentages. Students that are algebraic thinkers can mentally use their knowledge of numbers to decompose 5% into 1/100th times 5, and decompose 7 million into 7 times 1 million. Using the commutative property, one can justify that these two expressions are equivalent. However, learning to think in such ways is partially based on the experiences one develops in the primary grades. In the grades 6 through 9 classroom, students should have opportunities to use number sense to develop abstract relationships about numbers. For example, students need deep understanding of the meaning of fractions. Consider the following task. Without finding a common denominator, or cross-multiplying, explain which of the following fractions is larger. One way to solve this problem is to compare the unit fractions that form them. One can reason that 1/35th is larger than 1/49th, because if we cut a cake into 35 equal pieces, the pieces would be larger than if we cut the same cake into 49 equal pieces. Thus, since 7/35ths and 7/49ths both consist of 7 parts, and the parts of 35ths are larger, students can reason that 7/35ths is greater than 7/49ths. Furthermore, students can generalize beyond just one example. They might claim that if two fractions have the same numerator, the fraction with the smaller denominator is larger. Here's another task that provides students with opportunities to use the abstracting from computation habit of mind. What is the sum of the first 100 positive integers? That is, what is 1 plus 2 plus 3 plus 4 plus 5 plus so on through 100? One possible solution is that by pairing integers with sums of 101, like 1 and 100, 2 and 99, and so on, we can find that the original expression is equal to 50 groups of 101. Thus, the answer can be found by multiplying 50 and 101. The final answer is 5050. Ms. Shoemaker reviews a couple of related tasks before students begin working on a new task. In this first segment, the class reviews a task about triangles. The students were asked to find the perimeter of one triangle, then 2 triangles joined along one side, then 3 triangles, and so on. Let's listen as the students and teacher review this task.
But I want to take you even back to when the hexagon problem started. So we started with the triangle problem. Now I know you don't have this with you, so this is going to go on your prior knowledge. On the triangle problem, we were connecting equilateral triangles. So what was the first thing that we did to start this problem?
Drew a picture.
We drew a picture. So we drew one triangle, and then we drew 2, and we drew 3. And our object was to find the perimeter of the 100th triangle. All right, so what's the perimeter of that first triangle? If I just have 1, my perimeter was 3. And if I have 2, my perimeter is, don't think of the toothpick problem. We're only adding the outsides. I'm kind of backtracking. 4. And if I have 3, 5. All right, so our question is 100 triangles. 100 triangles all lined up together. What is my perimeter? 102. Now, the next step, we were looking for the function. How do I write the function for that? How do I write my function? So if I use the letter n, How would I be able to tell something if I had 950 triangles, my perimeter would be n plus 2. So I'm always adding 2. Now, why does that work? Why does that work? Why do I always take my number of triangles and add 2 to it? Why does it work?
Because in the triangles, when the 100 lined up, only half of them, only one side on both is going to be the perimeter, and then the extra 2 sides on the ends.
All right, so if I hear you right, you're saying out of all the triangles lined up together, one side's being used, so that's your N, and then
The 2 extra sides.
the 2 end sides. There's always just 2 end sides, so that's the plus 2. Does everybody remember that? All right, now let's go to the squares. Next, we went to squares.
After reviewing the triangle task, students went on to discuss a similar task involving squares. Then, Ms. Shoemaker introduced the hexagon task.
All right, now we're to the hexagon problem. This is where we left off. Does everybody have theirs? On our hexagon problem, said they called them trains. Train 1 has 1 hexagon, train 2 has 2, and they're all connected by one side again. Connected by one side. First thing we're computing is perimeter. And then we want to find, eventually, the pattern again. And this one asks us to find as many different ways as we could. So we're looking for not just one formula, but hopefully we can come up with a couple formulas.
In this task, students must find a rule for the perimeter of the nth train. What moves this task beyond the 2 previous ones is the fact that students must come up with more than one rule. This leads to the discussion of equivalent expressions, another essential component of abstracting from computation. Taken together, these 3 habits of mind form the basis of evaluating tasks for algebraic reasoning in all grades. Doing and undoing includes thinking about finding the input from the output, and working backwards to solve a problem. The features of building rules to represent functions include organizing information, predicting patterns, chunking information, describing a rule, using different representations, describing change in patterns, and justifying rules. Finally, abstracting from computation includes developing computational shortcuts, calculating without computing, generalizing beyond examples, finding equivalent expressions, using symbolic expressions, and justifying shortcuts in computational methods. Incorporating these features in the elementary and middle school curriculum will ensure that students are prepared to engage in algebraic reasoning in high school. Implementing tasks, maintaining cognitive demand. All teachers have been there. You think you've planned a great lesson, but then the students react in ways that, well, you just didn't expect. Consider this cartoon. I don't get this math problem. Let's use these Skittles to help you visualize. If I put 10 Skittles in front of you, then I ask for 6 of them back, how many Skittles would there be? None. Okay, let's try it with Brussels sprouts. As teachers implement tasks, it's important to keep in mind the learners and how they will understand and interact with materials used. Although using cognitively demanding tasks provide opportunities for students to think mathematically, research has shown that cognitively demanding tasks may not be implemented in cognitively demanding ways. A large-scale research project during the 1990s, entitled Quantitative Understanding, Amplifying Student Achievement in Reasoning, or QUASAR for short, documented the effects of incorporating inquiry-based instruction in economically disadvantaged schools. Based at the University of Pittsburgh, The project investigated a number of middle school math classrooms across the nation. The study partially focused on the kinds of tasks that teachers posed and the ways that they implemented them in the classroom. Based on the results, the Quasar researchers developed a framework to consider how tasks may evolve throughout the instructional process. First, tasks appear in written curricula or instructional materials. Second, tasks are set up by the teachers. This sometimes differs from the written curriculum because teachers choose to modify tasks or present them in a different way than the written materials. Third, tasks are implemented by students. Student interpretation may modify a task, or acts of the teacher while students work may modify how students interact with the task. Finally, the task in its written, intended, and enacted forms impact what mathematics the students have an opportunity to learn. Results of the Quasar research showed that when the teacher introduced high cognitively demanding tasks, and it was enacted by students in high cognitively demanding ways, student learning was high. Similarly, if the teacher introduced primarily low-level tasks, students engaged in low levels of thinking. This resulted in low levels of student learning. The most interesting finding is that if teachers provided students with high-level tasks and students did not engage in the tasks at high levels, the students' learning was moderate. This has an important implication for classroom teachers because it suggests that giving students opportunities to engage in cognitively demanding tasks produces better student learning results, regardless of how the students enact the tasks. Such findings confirm the goals of the National Council of Teachers of Mathematics, which posits that effective mathematics teaching requires understanding what students know and need to learn, and then challenging and supporting them to learn it well. Given that the highest level of student learning occurs when students engage in the task in cognitively demanding ways, it is important to consider how to implement tasks in ways that maintain the high cognitive demand of a task. The Quasar researchers documented at least 7 factors that were associated with the maintenance of high-demand tasks. For example, one method is teacher scaffolding of student thinking. By scaffolding, we mean that teachers pose thought-provoking questions to students in ways that preserve the complexity of the mathematical task. Let's see how Ms. Shoemaker scaffolded her students' thinking as a student tried to figure out whether 32 shopping carts will fit in a space 10 meters long.
Okay, is there a way to check your answer?
Yeah, you just plug 32 into the number formula.
What if your formula's wrong? Is there a way to check your answer?
32 times.
Think about how this is 32 cards.
31 times.
So how did you do 20 cards? Number 3. On number 3, we're finding the total of 20 cards. So if I think this is the answer for 10 meters, how could I check it to see if I'm right? What should 32.6 32 cards? If I work the question backwards. Okay, now you're saying 32 cards fits in here. How can I check 32 cards? So look at your picture. If I have 32 cards lined up, how many, what should the length be?
Ms. Shoemaker asked questions that helped her student figure out how to check his solution, without merely plugging the number into a formula. She encouraged him to work backwards and think about how he solved the problem for 20 cards. She didn't tell him whether he was correct or not, but scaffolded his thinking, which enabled him to figure it out for himself. In addition, the teacher must assist students to draw connections between important concepts. Connections can be made in multiple ways, such as connecting geometric and algebraic representations, or visual and written forms of expressions. For example, earlier we discussed how Mr. Smith used area models to help his students make sense of algebraic connections. Let's see how he helps students to make the connection between length, area, and the verbal representations.
And we need to review first what these tiles are named, just in case you've forgotten. These are all the smaller tiles, so you remember what the smaller, slender
Y.
rectangle? This one was the X. The Y was the longer one. You might see one of those in a minute when we get to our the activity. What about the little bitty squares? Those were 1. And the big square?
X squared.
X squared. Okay, so the shape itself gives us a little bit of a clue that this is the X squared and the X. X squared and X are different. That's the whole purpose for using this model. And when we named these originally, you may or may not remember this, when we named these all based on their area. And so the length of this side, every time we see this length, that length is called X. Every time we see the length of one of the sides of the little square here, that was called 1. And so to get the area of the slender rectangle here, we had 1 times X was X. Because we know for a rectangle we have the base times the height, or the length times the width gives us the area. So each one of these is named, and just to remind you, it's named based on its area. We're going to need to remember that the difference between area and perimeter, or the area, when we're talking about the area, we're talking about the inside part. We're talking about the space inside. But the dimensions of it are not the same. Like this X squared has the dimensions of X times X. And we're going to need to differentiate. We're going to need to remember the difference between the fact that this is X squared. We named it X squared, but the two sides of it are called X. That's going to be important in a minute.
Using representations is not enough to create students who are thoughtful algebraic thinkers. Teachers, like Mr. Smith, must help students connect their thinking in one setting to other settings. A third factor posits that students need opportunities to monitor their own progress. Students should be aware of what successful completion of a task will look like, and determine whether they have met instructional goals. A fourth factor requires teachers or capable students to model high-level performance. All students must be held accountable for high-level products. Teachers should pay careful attention not to accept incorrect or incomplete mathematical answers. Where appropriate, teachers or other students can model what would constitute acceptable, high-quality responses. Let's watch as one of Ms. Shoemaker's students explains how he figured out the total length of a row of 20 real nested carts to a fellow student.
What was the answer to number 3?
544.8. Take parts. You have to add this 3.7. You have to add it by 11 because this is 1 centimeter behind. So 11 plus 3.7 for the real distance would be 14.7. And since each cart on this is 1/24 of the real size, you have to multiply that by 24. Understand? So it'd be 14.7 multiplied by 24.
Peer modeling can be a way to maintain the cognitive demand of a task. A student that understands the task can explain his thinking to another student in a way that often makes more sense than the explanation that the teacher could offer. Mathematics is a subject in which justification and explanation are inherent. Teachers must press students to justify, explain, or provide meaning to the work that they do. Teachers can do this through their questions, comments, or feedback that they provide to students. The cognitive demand of a mathematical task has been shown to decline when students focus solely on getting correct answers, rather than explaining or justifying their work. Teachers should be wary to emphasize sense-making rather than correctness. Mr. John Searcy is a middle grades teacher at the Project School in Bloomington, Indiana. Let's observe as he and his students debrief an activity in which students found several fractions that are equivalent to 9/12. Notice the questions that he poses, and the emphasis placed on explanation and justification.
As I went around, I noticed several different strategies you had of getting equivalent fractions. And so I'd like to have any volunteers who'd like to write an equivalent fraction for 9/12 come up and do it. So Cordy, go up first, and I want you to explain what you're doing, okay? Okay. And how did you find 18/24? What did you do?
Well, I did multiplication. I did 12 times 2 and 9 times 2.
Okay.
I just added them both.
Okay, hold up. So we have one strategy is to multiply.
Multiplication.
What did you multiply? Tell me math terms.
I multiplied
What did you multiply by though? Delicious, that's right. Multiply numerator.
And I need to do one more. 5.
Don't even.
6.
Allison. Hey. Watch your mouth. Okay, and so how did you find 3/4?
Well, like,
There you go.
9/12 and, well, 9 and 12, you can both, well, they're both divisible by 3.
Okay.
So I just divided the numerator and the denominator by 3. So I just did the exact opposite of that.
What is that? 8,
Okay.
12. 1 half.
So Grayson, thank you, Allison. Does that make sense? So if we can multiply to get an equivalent fraction, doesn't it make sense that we can divide them both by the same number?
Students shared other solutions, such as 54/72, and provided their reasoning. Then, a student posed a new, more interesting solution.
Cordy, what else do you notice?
Well, I wanted to know about the 3/4 would be 9/12 because I thought that we did like 3 times 4 would be 12. So I thought it would, 3 times 8, well, 3 times 4 would be 12. So I thought it'd be 8/12.
So we're going to apply the same rule, because remember we said we want to come up with one rule or one algorithm that we can apply to every fraction every time. Okay, and so Cordy's pushing that. She's wondering, is this going to work? So let's say we do 3/4 times 4, and what do we get? 12/16. So the question is, 9/12 the same as 12/16? Why do you say yes, Elizabeth?
Because if 9/12 is equal to 3/4, I think anything between 3/4
Do you hear her proof, her mathematical proof? Because 9/12 is equal to 3/4, and anything equal to 3/4 is the same. What do you think about that? Yes or no? Does that make sense mathematically?
Yeah.
Yeah.
It makes sense, but I was just thinking that.
For some reason, too, this
It does feel.
when you add that step for most of my math students in middle school, that's been really tricky to be able to go backwards and then get a different number that doesn't necessarily line up with 12s. But that if you can figure that out, if you get that down, then you're working with numbers fluently. and you're doing some really great stuff. So to see this at the end of this math class gives me the goosebumps. You see those?
For each of the students presenting ideas, Mr. Searcy did not state whether the students' answers were correct or incorrect. Rather, he helped the students to see that their thinking was correct by having them explain and reason about the equivalent fractions. Teachers can also use paper strips, pictures, or diagrams to help students see the equivalence of fractions, and why the multiply numerator and denominator algorithm works. Instruction must be based on where students are currently at. Tasks should build on students' prior knowledge of mathematics and experiences in the world. For example, the task that Mr. Searcy provided for his students began by students reasoning about a fraction that was more familiar to them. Let's see how he began the class discussion on equivalent fractions.
So your math minute involves this fraction strip that's very curved. Okay, so this fraction strip right here shows the half mark. And so I want you to name 5 for 1/2. So instead of calling it 1/2, what are 5 other fractions that would still be at this point that have the name of half?
After giving students several minutes to think, Mr. Searcy calls on students to write different solutions on the whiteboard.
Yes, I do.
How do I know that 50 hundredths is a half? What's telling me that that's a half? Anastasia? 50 is half of 100. Is there another way to look at it? Allison?
50 plus 50 equals 100.
50 plus 50, 2 50s equal 100. Great. Okay. So finding equivalent fractions of halves is pretty easy. And so we want to use that same skill of looking at the numerator, looking at the denominator, looking at these as ratios, and finding equivalent fractions for all kinds of fractions today.
Again, we saw evidence that Mr. Searcy expected his students to justify their thinking. But he also was carefully setting up the task of exploring all equivalent fractions by building on knowledge that the students had already constructed about 1/2. Presenting tasks in ways that help students to build on their prior knowledge leads to maintaining the cognitive demand, and thus promotes student understanding. Finally, teachers need to ensure that students have sufficient time to engage in the task. Too little time will prevent students from wrestling with deep mathematical ideas. However, too much time can lead to off-task behavior. Based on research about cognitive demand, your challenge as teachers of students in grades 6 through 9 is clear. Make sure students have a steady diet of high-demand tasks, and that the demand is maintained as teachers and students interact with those tasks in the classroom. Implementing tasks. Planning a lesson. When designing a lesson that is inquiry-based, rather than teacher-directed, one structure to follow is the 3-part lesson plan: launch, explore, and summarize. In this episode, we'll see how Mr. Searcy leads a different group of pre-algebra students in an exploration of linear functions. Let's examine how he launched the task with his students.
Today I want to, you've learned a lot about how to recognize when an equation is linear, and I want you to be able to use what you know about linear equations and making graphs from those things to do something a little bit different. Okay? So in a minute you're going to be working with a group that will be randomly assigned, and I want you to do these 3 things. I'll make sure you get them in order. So the first thing, and I'm not going to give much instructions outside of this, I want you to rely on your group members to get this assignment down. The first thing is I want you to write equations lines that form a triangle. Okay? Exactly. I'm not going to explain that. That gives you all the information you need. Okay? I'll get you graph paper in a minute once I get you into groups. But I want you to write equations for 3 lines that form a triangle.
3 linear lines.
Yeah. Does that make sense? Because you said lines twice, linear. But it's beautiful. I like that. Step 2, I want you to sketch the graphs and label the coordinates. Do you know what this word is of the vertices? The triangle. What does it mean when I say the vertices of the triangle? Morgan? Yeah, the points of the triangle. So where 2 lines come together, you want to label those coordinates, right? And it will be something like x first and then y, right? That's a coordinate. Does that make sense? And then number 3, I want you to ask this question, I want you to answer this question. Will any 3 lines form a triangle? Let me update that. Will any 3 lines intersect? Alright, so that's all the information I'm going to give you. The only other information you need is to go ahead and divide it into groups. So I'm just going to randomly assign you to 6 different table groups, okay?
Mr. Searcy made sure that his students understood the task before they started to work in small groups. He answered students' questions about the task, clarified unfamiliar terminology, and established clear expectations for working on the task, such as an expectation that students would work in groups to solve the problem. The launch portion of a lesson can be used not only to make sure that the task is understood and to establish clear expectations, but also to activate prior knowledge needed to complete the task. During the exploration time, students discussed the problem in small groups. Mr. Searcy moved about the room, scaffolding student thinking as needed.
What do we equal if I do that? Well, let's see how the equation for it. Okay, so y is a. Y is a. So a equals y is over here.
I did try to suggest the
Oh, that's like, how about instead of multiplying, we should subtract. Subtract 1. Y equals x. No, x plus 1. Mine goes up all.
Do you have to make a table?
Well, I did.
Which line did you make a table for?
Oh, there's this line right here. This line right there, the bottom one. There's no linear.
There is a.
Well, yeah, but not according to this.
Like, what are you doing each time to get these? Like 4?
Well, like 4 doesn't really make sense. I don't know. Because 4 and that is 4 right here. But on that one, 6 is also really close to 4. You'd have to go precise. And since it's diagonal, I can't really go precise. Well, I guess I could if I did like. Well, I might as well just change my triangle. Because otherwise I'd have to change it to 1.5 and stuff to get really precise. So I'm going to change my triangle.
Mr. Searcy allowed the students to work on their own in small groups. As these students' discussions demonstrated, the students were engaged in the act of true problem solving. There was no clear method to find a solution, and the students were required to use prior knowledge coupled with logic and reasoning to find an answer. Communication between students played an important role in the learning process. During the explore portion of a lesson, it's important for the teacher to let the students work on the task while carefully listening, posing questions, and providing hints as necessary. Sometimes during this part of the lesson, a group of students finishes early or becomes bored with the task. At that time, the teacher may want to consider providing an appropriate extension to the problem. For example, in Mr. Searcy's class, if students found one solution that involved both a horizontal and vertical line, he could have asked them to find a triangle in which none of the lines are either horizontal or vertical. After the students worked on the task in their small groups, Mr. Searcy asked students to think about and share what they found challenging about the task.
Asia?
At last, like the first two ones that we do are pretty easy, and then it's just the last one. It's just the hardest, because you have to decide it.
Wait, I'm confused now. So you said the last two are the easiest and then the last one?
Oh, not that, man. I'm talking about the graph, the triangle.
Okay, so which?
It's like the last one is the hardest.
The last line?
Yeah, the last one it ties together. Like the first two triangle points, like this, and then it's the last one that's the hardest. Because, I don't know, it's the hardest.
Sage?
I don't know how to get the equation out of anything of this. I got the coordinates and stuff,
It's like, yeah, I think it's just first. Yeah, that's the big thing.
So we've been able to write an equation. I have you two, I'm going to get you two. We've been able to write equations really easily from tables. But now we've got to figure out, well, if I have a line, if I'm making my own graph and have a line on the graph, how do I make the equation from that line? Sage and then Sophia.
Could we make a table out of the coordinates?
Did anybody try that? Did anybody make a table out of the coordinates? Did that help you make an equation?
No, they did with the first one.
It helped you make an equation?
Yeah, still makes sense.
Okay, so that's a hint that we can take back to our groups, is to write the coordinates into a table and then to see if that helps us make an equation. Sophie?
During the course of the discussion, one student presented an idea to use a table to organize the information. After several other students shared their frustrations, Mr. Searcy summarized the conversation by having students consider how they could use tables to help organize the information.
But let's look at, we have some clear, we really have gone through and identified frustrations, right? We've been able to find what we can do to help. So with writing the equation from a graphic coordinates, we've got the hint that we can take the lines. If we have, if this is 1, this is 1, right? Let's say this is 2 and this is 2. This is 4 and this is 4. Can't we make a table out of this and say that 1 is 1, 2 is 2, 4 is 4, okay? Would you be able to make an equation out of that? What equals what in this scenario? What's the equation? Gunnar?
Wouldn't it be plus or not plus equal itself?
Okay. That's it. Okay. Times itself? Okay. All right, let's think about that.
Times 1.
Times 1. And how do we show times 1 for a variable?
You could put x times 1 is
x times 1 equals y. Remember we talked about another way of showing x.
During the summarized portion of the lesson, Mr. Searcy prompted students to share their frustrations and the challenges that they encountered while solving the problem. By having his students think about the problem, students had the opportunity to present possible solution paths. Note that he did not use the summarized portion of the lesson to solve the problem for his students. Even though not all students solved the problem, he did not take over the work for them, but rather discussed possible solution strategies. The summarized portion of the lesson is a time to promote whole class discussion, listen actively to student solutions, and emphasize the key points or main ideas in the lesson. This portion of the lesson is very important and should not be ignored or cut short. It is during this time that students learn from each other and form connections between different approaches used. The teacher plays an important role in orchestrating the class discussion and prompting students to share strategies. Assessing student thinking. Questioning techniques. Formative assessment is any assessment task designed to promote students' learning. These tasks give both teachers and students feedback so that teaching and learning activities can be altered according to the results. Formative assessment is different from summative assessment, the goal of which is to measure mastery. Formative assessment is thus assessment for learning. It is a type of assessment that drives instruction. As you think about formative assessment, it is good to consider where your students currently are in their understanding, where they are heading, and how you will get them there. Questioning students is one means of formative assessment that can provide you, the teacher, with that information. Let's take a look at different types of questions and the purpose of each. Assessing questions are those that clarify what the student has done and what the student understands about what they have done. For example, you might ask, "How do you know?" Or, "Can you show me where this came from?" Advancing questions, on the other hand, move students beyond their current thinking by pressing students to extend what they know to a new situation. This type of question will often begin with, "What if?" The third type of question is one that manages or focuses the student. Examples of this type of question would be, "What do you know? And what do you need to know?" Or, "Is there a way you could organize your work to help you notice patterns?" Today we will see examples of teachers using the first two types of questions. In this clip, we revisit Ms. Shoemaker's class. Here, we see her using assessing questions to help her clarify if her student understands where the 11 came from in his solution to the question, what would be the total length of a row of 20 real nested carts?
What we did like timeless length of this is we took 11 times the space in between those, which would be
11 centimeters. Then we added it.
Why,
11.
wait a minute, why 11?
No, no, because 11 things behind it. Can you still see what you're doing?
Yes, I'll be right over.
It's 11 times 24. Anyways,
But we want 20 cards.
yeah, we did that.
Okay, that's what I'm trying to get him to explain is where did this answer come from? You need to write out where that answer came from, because I don't think everybody in your group's on the right track on where that answer came from. So think about it.
The student was probably referring to the 12 carts in the diagram, but Ms. Shoemaker wanted to make sure he understood where the 11 came from. Through the use of assessing questions, she was able to help the student clarify what he understood and what still needed further explanation. In this clip, we revisit Mr. Searcy's class as a small group discusses how to determine the equation of a given line. As you watch this video clip, notice the types of questions Mr. Searcy poses.
Tell me about how, if that's on a graph, if you saw that line on a graph, how would you describe that rate of change? It's linear, yes. But how would you describe that rate of change?
One of them should be going backwards. No, like this.
Put a line that's going up.
Going up the change would be positive.
How do you show that in an equation?
This one should be going up.
Or,
So if we multiply,
Should be going down.
okay, let's make sure Emma's understanding.
okay, so
Yeah, I mean, with that, I mean, just make up any, yeah,
shouldn't we?
yeah. So like I could do -4, point negative, like -4 multiplied by -4 on the graph. Or like -5 on the graph multiplied by -5, which is -3 on the graph.
I want you to try graphing those and see if that gives you the line that you drew.
But we don't have graph.
You don't have graph paper. JD, I know you made graphs without graph paper.
Mr. Searcy advances his students to reflect on the concept of rate of change as they struggle to determine the equation of the line. In doing so, he is moving students beyond their prior explanations, which did not focus on rate of change. When the students tried to describe a potential method, he did not tell them they were right or wrong. Instead, he told them to try to determine whether it worked. Here's a task we used earlier as an example of building rules. If your students were working on this task, what are some questions you could ask to assess or advance your students' thinking? Take a moment to jot down some ideas. Here are some possible questions you might ask. At the beginning, how many sheep were in front of Eric? After one sheep is shorn, how many sheep are in front of Eric? How many are behind? What about after 2 sheep? How could you keep track of your work to show what happens after each sheep is shorn? When working on mathematical tasks that require complex thinking, students will often throw up their hands in frustration and say, "I just don't get it," or "I just don't know where to start." Instead of telling them what to do, try some of these questions. What don't you get? What's confusing? Where did you get stuck? What makes this problem hard? What would make this problem easier? Asking these types of questions can diffuse the situation and help the student to focus on what they do know. We have covered a lot of information. We looked at analyzing tasks through the lens of cognitive demand, the kind and level of thinking required of students in order to successfully engage with and solve the task, and algebraic habits of mind, doing and undoing, building rules to represent functions, and abstracting from computation. We then looked at implementing high cognitive demand tasks, how we maintain the level of cognitive demand, and how we successfully plan a lesson around that task. Finally, we looked at assessing student thinking through the use of questions, assessing questions, and advancing questions. We would like to invite you to consider how to incorporate the ideas shared in this presentation into your classroom. Use the following guidelines for you to consider how to get started. First, choose an existing task from your curriculum materials. Analyze the task for cognitive demand and algebraic habits of mind. If the task does not provide students opportunities to build connections or engage in problem solving through doing mathematics, consider how you can modify the task to increase its cognitive demand. Next, anticipate the types of difficulties or misunderstandings that students may encounter when engaging in the task. Finally, plan appropriate scaffolds and questions to react to students. Thank you for taking the time to listen and learn. As you put this knowledge into practice, remember that it will take time to feel comfortable with this new approach. but the benefits for your students will be worth the effort.